My name is Rafi Krikorian. I run a group at Twitter that we call Platform Services. So effectively, Platform Services is the core scalable infrastructure of Twitter. So we run things that are called the timeline service, or the tweet service, or the user service, or the social graph service. So we run all the machinery that powers the Twitter platform. And we use it to expose APIs, both internally and externally. So internal clients all use the same APIs effectively that the external third-party ecosystem uses. And there's like 1 point something million registered apps against our third-party APIs. My contract with the product teams at Twitter is basically don't worry about scale. Like my team will sort of handle that for you, and then we'll just sort of make sure that Twitter can scale to whatever you guys need it to do. So we work very closely with capacity planning. We architect all the backend systems. We're constantly replacing infrastructure as the site grows to places in ways that we didn't think it would grow before. I'm also the current chair of Twitter's architecture group. So my team there thinks about the overall holistic architecture of Twitter, and we maintain things like the technical debt list and stuff like that. Basically, the stuff that we kind of want to get rid of our architecture to try to prune it down to what we really want it to be. And what we want it to be is no longer a web app. Like we want it really to be a set of APIs that power mobile clients worldwide. It'd be one of the largest real-time event buses on the planet, and try to really think of how to redefine what most of you think of as Twitter and bring that internally inside the architecture. So what I want to do today is at a high level talk about how we do timelines at scale, but sort of be almost a random walk through our architecture a bit, just try to show you how we've sort of laid this thing out, specifically to how we serve the home timeline or the search timeline or things like that. So I think, how many of you use Twitter in the room? Okay, well, that's great. Just as like a high-level overview, obviously, you all know what Twitter does, so I'll only spend a second on it. But the goal of Twitter to most users, and the way I explain it, is that people are creating content all the time on the Twitter platform, and then the job of the Twitter platform is to figure out how to syndicate this content out. So how to send it to that one follower who might be following you or the N followers that might be following you. Our real challenge is really the real-time constraint around Twitter. Like, it's unacceptable for us to have messages to get to our users in anything more than about 5 seconds. Not saying we do it in 5 seconds all the time, but that's sort of like our acceptable boundary of what we're trying to get done. And this means delivery in lots of different ways for us. Delivery for us means getting it into all the in-memory timeline clusters that we maintain, which is what I want to talk about today. But it also means all the push notifications that we do, all the emails that we trigger, all the iOS notifications, BlackBerry, Android, SMSs. We're I think, currently the largest generator of SMSs on a per active user basis in the world. So we're just sort of, delivery for us means getting content in and then sort of exerting pressure on the internet to try to get them back out again as fast as we possibly can. As you can imagine, days like Tuesday on the election night get kind of crazy at Twitter because we have some of our biggest spikes in Twitter content coming in, but also some of the biggest fan out of content going back out again. I think we were seeing like a ridiculous increase in the number of emails we were generating on Tuesday night. We hit, I believe, the second highest number of tweets per second number was on Tuesday night. So creating infrastructure to do that is basically my team's job. So I want to sort of tackle this problem in a few ways in explaining this. But I think first it's helpful to explain what makes up the home timeline. I've put up this slide in a few talks before, but I like to just sort of walk people through it just so people remember, because it's a little subtle what we do. So there are two main types of timelines that users interact with at Twitter. So there's what we call the user timeline, and that's all the tweets a particular user has sent. So I have 3 user timelines on the screen. From left to right is my friend Nelson, it's Tim O'Reilly, and then it's the QCon New York timeline. And what the home timeline is basically a subtle merge, a temporal merge of all these user timelines of the people you're following. There are some business rules around it. For example, we might strip out some @ replies that of people that you don't follow. Our at reply logic is a little complex. Basically, if you at reply someone, no one else will see it unless you're also following that person you at reply. So we have to take into account some visibility rules and what we want to actually display to the user. And then there might be other things, like you may be turning off retweets from a particular user. Like I may not be following Tim O'Reilly's retweets, but see his regular tweets. So once we strip out some tweets, then basically the home timeline is just that temporal merge of all those tweets. Of course, doing this at the scale of Twitter gets a little complicated and a little challenging, and that's I think, what I'll spend most of today chatting about. So we divide up what the users see from their home timeline, from Twitter in a few ways. So we have what we call the targeted timeline, and that's things like twitter.com and the home timeline API. It's things that you've personally curated, and these are tweets that we're going to deliver to you because you've asked to see them. We deliver them in a few different ways. One of them is a pull-based mechanism. So you can think of twitter.com or the home timeline as a pull, right? I'm going to twitter.com or I'm making a REST API call against the home timeline API and requesting this data of Twitter, who then needs to deliver me that data. We also have what we call the queried timeline. And for us, mainly that means the search API. So you're going to issue a query against our corpus. We're going to figure out all the tweets that we can return that match your particular query, and we'll return it back to you as fast as we can. Again, pull-based is sort of like search API or going to search.twitter.com. The two I'm not going to spend that much time talking about today, but I just want to highlight, is also the push infrastructure of Twitter. So we run some of the largest, like I said before, one of the largest real-time systems. And what it means to be really real-time is that you can actually open a socket to Twitter, and we'll push tweets out to you as they sort of come in. So in about 120 to 150 milliseconds after a tweet's created, we can route a tweet out of an open socket. At any given time, there's about 1 million sockets open to the push cluster. And these are things that like we call the fire hose. So a lot of search engines license the fire hose from Twitter, which means all public tweets are getting routed out of that socket. Most people don't do that, partially because it costs money and partially because it's something like 22 megabytes a second these days. So most people just can't keep up with a fire hose. But things like the user stream connection, which powers TweetDeck or powers Twitter for Mac or some of the other streaming clients, also come out of here. And what we do there is when you log in, we actually look for your social graph, and we'll only send messages out from people that you follow. So we can actually recreate the home timeline experience, but instead of polling, you get it on a persistent connection. And then we also have a pushed version of the queried API. So you can issue a standing query against Twitter, such as give me all the tweets that match Coca-Cola, or all the tweets that match Twitter, or all the tweets that match election 2012. And as those tweets are being created, we'll route it out the sockets that have registered that standing query. But we're not going to talk very much about the push side. I want to focus mostly on the pull side today. So just to reiterate the challenge for a second, and the challenge for engineering, is there something like 150 million worldwide active users on Twitter right now. We're doing over 300,000 requests every single second for timelines, whether it be the home timeline or the search timeline. And most attempts at what we call naive materialization just don't work. And what I mean by this is sort of the example I like to give to undergrads whenever they say, I can build Twitter, is sort of like doing a massive select statement over a MySQL table or something. Trust me, Twitter has tried that, and it doesn't really work very well. So what we've done instead, and what I'll talk about for the rest of the time, is sort of take the right-based fan-out approach to getting all tweets delivered to all our users. So we actually do a lot of processing on tweet ingest and figure out where those tweets need to be delivered to, and then we make the read time really easy. So we're no longer doing any computation on reads. As you can see, our read rate gets really quite insane, whereas our ingest rate is something more in the order of 4,000 queries a second. I'll get more of that later. So if we just sort of go through a high-level architectural diagram, a tweet comes in. This is ignoring a bunch of other pieces of machinery that Twitter has. So we obviously have load balancers in place. We have something we call the TFE, which is a Twitter front end in place. But abstractly, a tweet comes in, it hits the right API, and we immediately start a process that we call fan out. So fan out takes all the tweets that come in and start placing them into a massive Redis cluster that we have in all the data centers. We obviously replicate this many times, so every single tweet is actually stored 3 times in 3 different machines in the Redis cluster. At Twitter scale, 1 machine a day, give or take, is probably flaking on us, so we want to make sure we have everyone's home timeline. The way fanout works is once a tweet comes through, we actually query the social graph service. There's a system we call Flock. Flock holds all the followers and followings of people at Twitter. So it knows that I follow about 700 people, and knows about 20,000 people-ish follow me. So every single time a tweet comes in, the fanout daemon queries Flock and then starts iterating through all the timelines that we store in the Redis cluster. So that kind of looks something like this. So we're actually using native lists inside Redis. And in every one of these lists, effectively, we're keying the user ID of a destination against an array of effectively the tweet ID of all the tweets that are coming in. Let me back up for 1 second. So I tweet. There are about 20,000 people who follow me. What the fanout daemon is going to do is look up the locations inside the Redis cluster for all 20,000 of those people. It's a little more subtle than that, but all 20,000 of those people, and start inserting that tweet ID into all those lists throughout the Redis cluster. So basically, on every single write, as many as 20,000 inserts are occurring across the Redis cluster, and we're storing the tweet ID of the tweet I generated, the user ID, which is my user ID, and some miscellaneous bit fields that we use for product purposes, marking whether it's a thing like a retweet or if it's a reply or some other event that most users don't care about, but we need to keep track of internally. And we store a list that's approximately 800 IDs long. So your home timeline right now, if you were to log into Twitter, your home timeline is in one of these Redis machines in the data centers, and you have an array of about 800 tweet IDs sitting in it right now. And these are all the tweets that compose your home timeline. The trade-off here, obviously, is that your home timeline then stops at 800 IDs. If you page back through Twitter long enough, you'll hit the cap of about 800 tweets to make up your home timeline. We just won't go back any further. So that's one product decision we'd have to make because of the size of this Redis cluster. We have a couple of terabytes of RAM just in this Redis cluster alone, and we're trying to hold every single active user in memory at any given time to try to keep latencies down. So sorry, you just can't hit more than 800. But one optimization that we've done is if you're not an active user, and we define active user as having logged into Twitter once in the last about 30 days, it changes depending on cache capacity or how popular Twitter was in the last few weeks, we actually don't bother sticking that tweet ID into cache. So only if you've been logged in the last 30 days do we do that. One thing I haven't mentioned here is that when the tweet goes through a fanout process, not only are we iterating through Redis, we actually do store it in disk, obviously. But the only thing that actually hits disk at Twitter is your user timeline. So the index of all the tweets that make up my timeline hits disk, but none of your home timelines hit disk. Your home timelines are only in the Redis cluster right now. If you were to fall out of the Redis cluster, then we go through a process that we call reconstruction. And reconstruction is basically a query against the social graph service, figure out all the people I'm possibly following, hit disk for every single one of them, that big SQL statement effectively, and then shove them back into Redis as fast as we can. It's not actually it is actually MySQL at the bottom, but you don't issue a select query. We have a layer on top of MySQL that we call Gizzard, and Gizzard abstracts away most of the actual MySQL transactions that you have to do. It also provides us global replication and things like that. So this is where your home timeline is currently sitting right now. If one of these machines were to have a problem, that would suck because we'd have to reconstruct all the timelines of every single person that was on that machine, hence why we replicated 3 times per data center. The probability of those 3 machines going offline is pretty small for us. And if one of these tweets is a retweet, then we actually store a pointer to the original tweet just for easy querying purposes. When you actually then go look up your home timeline, if you were to come log into Twitter and issue a request for your home timeline, what's occurring is we actually do a hit against a system we call the timeline service. The timeline service then only needs to find one machine that has your home timeline on it. So effectively, we're running 3 different hash rings. So we have your home timeline 3 different places. We just go through them, and we'll find the first one that we can get fastest, get your home timeline back out, and return it out to you as fast as we can. That's what powers Twitter.com when you actually go to the website. So the trade-off we've made here is that that fan-out process might take a little longer, but this read process to the end user, I think our rendering time in San Francisco is about, from cold cache from a web browser that hasn't cached into JavaScript, it's about 2 seconds right now. The API call is about 400 milliseconds. So the call at the edge of the data center is on the order of about 100 milliseconds, so transit time. So we can do the lookup of your home timeline extremely quickly and extremely efficiently because we've stuffed all your home timelines to this massive Redis cluster for us to take a look at. So this is what makes up your home timeline, and this is how we serve most of the web traffic that we get, whether it be web API traffic or render traffic. Just to provide a little more color, like as I said before, your home timeline only contains the IDs of the tweets. So we actually still have to what we call hydrate those tweets to provide you the full context. We've entertainingly named those services GizmoDuck for the user objects and TweetyPie for the tweet objects. So given an array of those IDs, we can multi-get against either TweetyPie or GizmoDuck to give the full rendered content that we might display to users. Each one of these services has their own caches. In fact, I think GizmoDuck at any given time has the entire user base of Twitter inside its Memcache cluster. And TweetyPie has about the last month and a half of tweets stored in its Memcache cluster. So we expose these to internal developers, so anyone at Twitter can build features that depend on that pieces of content and not really have to worry about the rate at which they hit it, because we have abstracted away the disks for them. So that sort of covers how we do the pull-based timelines at Twitter. And the thing I wanted to also chat about is how we do search at Twitter. So this is a very directed path. It's a completely pre-computed home timeline. All the business rules we execute as the tweets come in for visibility purposes. We might do a little read time filtering at the edge. So we have this quote-unquote feature where we withhold content in certain countries. For example, Nazi content can't be shown in France, for example. So we do read time stripping of that content as the timeline is served out. But besides that, everything is pre-computed as the tweet comes in. Search, on the other hand, is the exact opposite. Search is all computed on the read path, and it makes the write path really simple for us. But it looks remarkably the same. So as a tweet comes in, we have a system that we call the ingester. And the ingester does what most search ingestion systems will do. It tokenizes, it figures out the features, it figures out everything we want to index against, and stuffs it into a single early bird machine. Early bird is a modified version of Lucene for us. And we store in all the early bird clusters a massive Lucene index in RAM. The nice thing, though, is that for fan out, every single tweet might be stored in N home timelines, depending how many people are following you. Every single tweet in the early bird cluster is only stored in one early bird machine. We might replicate it for load purposes, so we can sort of like distribute load across the different machines, but it's only stored in one place. That means, though, when the Blender comes and hits looking for requests, Blender is what creates the search timeline for us. It actually has to scatter gather across the data center. So we actually query every single early bird shard, or one of every single early bird shard, and start asking it, do you have content that matches this particular query? So if I'm asking for a New York Times query, I'm going to actually ask every single early bird shard whether or not it has anything for New York Times. I'll get all the results back. I'll sort, I'll merge, I'll re-rank. I might ask for some social proof. Twitter's main way it does ranking is by looking at the number of retweets, favorites, and replies a tweet has. So we have all that data on another cluster, so we can get that in, re-rank stuff, and return it back out. actually we compute all that activity information also on a write basis. So as your guys are favoriting and replying to tweets, we actually have what we call an activity timeline internally. And that's similar to the home timeline, and that's just a series of IDs of pieces of activity. So I have a favorite ID, I have a reply ID, and things like that. So we feed all that information to the blender, and on the read path, it recomputes, merges, and sorts to return what you would see as the search timeline. We also power the discovery page off of the blender. So discovery is basically it's a customized search for all you all. We know a lot about you. We know a lot about you because you guys follow a lot of people. We know a lot about you because you guys click on a bunch of links on Twitter. So we use that as part of the discovery basis. So you're effectively issuing an implicit query against Twitter whenever you go to the discovery page. So for example, if I were to go to the discovery page, it knows that I like San Francisco, I like New York City, I like biking, I watch politics, I'm a fan of romantic comedies and sci-fi, and it can re-rank any query that comes through and show you just that content that matches that implicit query that comes in. So those two systems look remarkably the same, but they have a property that's inverted from each other, like I was mentioning before. So if we look at the way the home timeline is generated, so we have the write API, and we have a bunch of Redis clusters. As a tweet comes in, we go through an O of n process to write to all the different Redis clusters, where n being the number of people you're following. So if number of people are following you. So 20,000 people follow me. I'm going to iterate through 20,000 different inserts potentially across the Redis cluster. This obviously gets pretty bad if you go to people like Lady Gaga or Barack Obama. Then we're doing a couple tens of millions of inserts across the Redis cluster. But the benefit is if you're, so if we look at the search timeline for a second, when a tweet comes in, we hit the ingester, we only need to go to one early bird machine. So our write time path is an O of 1 write. So it's a fairly bounded write. Like we ingest a single tweet in under 5 seconds these days. So a tweet comes in, do about 5 seconds between the QA and the computation, and we find the one early bird that we need to stick it into. On the read path, on the home timeline though, Rafik Krikorian logs into Twitter. I issue a request for my home timeline, whether it be the API or the website, and I find the one Redis box I need to return. So I have an O of 1 read. We've optimized Twitter to be highly available on the read path for your home timeline. That's what most people are doing. Twitter is very much a consumption mechanism. It's not a production mechanism. If you look at, as I was saying before, if you look at our numbers, we do 300,000 requests a second just for reading, whereas we only do maybe 6,000 requests a second for writing. And on the search path instead, a single read across the blender does an O of n read across the entire cluster. But most people don't use search, and this way we can actually be much more efficient on the search cluster for how we want to store tweets across it. But we pay for it in time. So on the read path of the home timeline, as I was saying before, I can do it in tens of milliseconds. On the read path on the search timeline, I'm doing it on the order of 100 milliseconds. So we're paying for it in cost. Also, on the write path, all the Redis clusters here are backing disk. So we have the tflock cluster, which actually contains all your user timelines to disk. And the Redis cluster is basically masking that read for us. We just never have to hit disk. Whereas on the search cluster, we actually never hit disk. The entire Lucene index is stored in RAM in the search cluster. So we can just scatter, gather, and make a very efficient read across the entire data center because we just never have to hit a platter anywhere. There's a question. Yeah, so the question is, where do we store the actual text of the tweet? So we have another system. Text of the tweet is actually kind of irrelevant to most of our infrastructure within Twitter. Like we actually do textual insertion right at the edge, right before we render back out. We have a whole other cluster that we call T-Bird within Twitter, and that's just storing the entire corpus of all the tweets that have ever been created. So when I refer to the IDs of a tweet, and you can multi-get against a tweet service, most of the text of the tweet is stored in RAM. And if it's not, then we can hit the T-Bird cluster to actually do the select query to get it back out again. But for most of the purposes within Twitter, actually the text of the tweet is almost irrelevant to us, except on the search pipeline and potentially on the the trends pipeline or the what's happening pipeline or things like that. Home timeline doesn't care about the text of the tweet almost at all. So to go into some of the things that we've been experimenting with at Twitter is how to actually make this pipeline even faster and more efficient than what we're doing today. So the problem I was mentioning before is that fan out can get quite slow. Like I'm trying to do it under 5 seconds, but that doesn't really work sometimes. And it gets really hard, especially for when celebrities tweet, which is happening more and more on Twitter right now. So if we just look at the pipeline that we're sort of trying to go through, just to refresh your memory, this is sort of how the Twitter follow graph works, is that it's an asymmetric follow, so all my tweets are only rendered onto people who are following me at any given time. I mentioned before, we know a lot about every single user, and this is actually how we know a lot about you. Twitter knows a lot about me because I follow Lance Armstrong, but Lance Armstrong doesn't follow me back. So there's an implicit social contract if there's a bidirectional follow. If that bidirectional follow doesn't exist, then we can imply a lot of data about the user. But so when the cardinality of this graph gets really large, it's because someone's followed a lot. And those are the people that we have the hardest time actually fanning out tweets for. So if we look at some numbers just very briefly, like these are some of our highest followed people right now. So every single time Lady Gaga tweets, about 31 million people need to have timeline deliveries occur. I would try to do that as quickly as possible, but that's a lot of phones, a lot of emails, a lot of everything we need to do within the data center. So it gets even worse, obviously, when two of these people start talking to each other, which also happens all the time. So the challenge of doing fan out for one of these high valued users is actually the biggest problem for Twitter. And it's because it actually introduces race conditions all across the site. If we sort of think about a single tweet from Lady Gaga going out, if that takes on the order of minutes to be fanned out, which does occur, then people are starting to see her tweet at different points in time. So you kind of want tweet fan out to be as instantaneous as you can possibly pull it off. But the person who followed Lady Gaga most recently will see her tweet potentially 5 minutes before someone who followed her far in the past. Interactions could start occurring in that tweet. Fan out happens on a multi-process basis in parallel across the data center. So it basically means Lady Gaga sends a tweet. I potentially get this tweet really early and reply to her tweet. Another process is handling my fan out while the Lady Gaga fan out is still occurring, and my tweet is injected into someone else's timeline before Lady Gaga's tweet is delivered there. So people are seeing replies before they're seeing original tweets all the time across celebrities on the clusters right now, which causes much user confusion, as you can imagine. What we tend to do is re-ranking or reordering of tweets right as we deliver it. So we'll do a simple sort on tweet ID, because tweet IDs are mostly monotonically increasing. So we can do a simple sort on tweet IDs right before we deliver it out, just to sort of cheat for a second. But at scale, obviously this gets pretty large. This is actually a dump of what we call the garden hose right behind it. But there are about 400 million tweets a day being pumped through the system. And just at that scale, executing fan out becomes problematic for us. The queues back up all the time. And trying to get through high-valued fan out, if it takes on the order of minutes, means that we're burning processes all over the data center to try to get through the high-valued users. So what we've been trying to do recently is figure out how to merge the two different paths. So we have one path, which is the search path being read time reconstruction, and we have one path being the home timeline path, that's write path construction. What we've been trying to think about is there an opportunity to do both in certain cases? So if we looked at a simple tweet, let's say a hello world tweet, on the search index, we're going to tokenize it for indexing on every individual word, so hello and world. But on the home timeline path, we're basically creating a fan out index based on every single user who's following the author of the tweet. So in this case, if it was me, Dana Danger is one of the users who follows me. So if we look at it that way, so we're trying to create an index, then the search problem becomes fairly interesting for all of us. So if we user intent of hello world, if we were to do a query for it, then it sort of expands out to a hello and world query. But if I'm looking for my user timeline or my home timeline, that could effectively be a query for the home timeline of Rafi Krikorian. Home timeline of Rafi Krikorian expands out effectively to the user timelines of everyone I follow, just union together. So what we've been recently experimenting with at Twitter is taking something like the home timeline and then not fanning out the high-value users anymore. So people like Taylor Swift, who might have a couple tens of millions of followers, don't bother executing fan out on them anymore. Instead, execute fan out only people who have small number of followers, basically the long tail of followers, and then at read time, merge in Taylor Swift's home timeline or merge in Lady Gaga's home timeline. So we don't spend computational resources fanning out this large number of tweets from a single person, and instead just do read time computation. This is providing us a nice balance between write path and read path that actually is making the system a lot more efficient, and is saving tens of percents of computational power across our data center. So this is one of the things that we've been experimenting with pretty heavily within Twitter. There are two other paths, like I mentioned before, which are sort of the push paths and the offline batch processing at Twitter. I'm not going to bother covering that very much here, but I just sort of want to illustrate it so you have the entire view of what a single tweet might do once it hits the data center. We forked off tweets in many different ways within Twitter, mostly to decouple teams from each other. So the search team can work pretty independently of the team that works on the home timeline, which works pretty independently from the push team, which works pretty independently from the team that generates your interest emails that you might be getting a few times a week. But for performance reasons, just to go back to this for a second, we've been also decoupling the entire system from each other. Twitter used to be fully synchronous. That stopped about 2 years ago just for obviously performance reasons. Right now we have what we call the synchronous path of Twitter. So if you try to ingest a tweet into the tweet API, we can ingest in about 130, 145 milliseconds, and then we disconnect all the clients. This is for legacy reasons. Our write path is actually still all powered by Ruby right now, and it's actually all powered by the MRI. MRI being single-threaded, unfortunately, means that we are burning CPU power every single time one of these unicorn workers are being eaten up. So we want to be able to release the connections to our clients as fast as we possibly can. So a tweet comes in, Ruby ingests it, sticks it in the queue, and then disconnects. So this way, we only run about 45, 48 processes per box right now. So that means we can only ingest about 45 to 48 tweets simultaneously per box. So we want to disconnect as fast as we can, and then hand it off to the asynchronous path of Twitter. And this is where everything I just talked about sort of kicks in and sort of runs as this background process, running as fast as we can. The query path is obviously also where we return a bunch of data. So we're really concerned about the performance of this system. It's one of the things that I look at every single day. We have dashboards all around the Twitter office, just trying to understand how the system's performing at any given time. So just to reiterate a few statistics before I show some graphs. We have about 150 million active users. If you have about 1 million, sorry, that slide got a little messed up, but if you have about 1 million followers on Twitter, it'll take us a couple of seconds to fan out all those tweets. So this is what tweet input looks like right now. We obviously spike to fairly large events. I think around the elections, we hit somewhere in the order of 15,000 tweets a second were being pushed through Twitter at any given time. And then fan out starts, where we're delivering about 30 billion tweets a day right now. So a tweet comes in, multiplies across the cluster. If you have about 1 million followers on median, it takes about 3.5 seconds right now to deliver to every single one of your followers. It gets pretty bad on the scale of Lady Gaga, where at P99, it might take up to 5 minutes to finish timeline deliveries. But on average, we're doing about 300,000 requests a second. And just to talk about the performance for a second, so We have a system internally that we call Viz that monitors every single cluster at Twitter. So if we were to look at basically what the median request time to a timeline service for the home timeline is, we're clocking, I think, about 5 milliseconds right now to get that data out of the Scala cluster. And if we looked at something like P99, then we're coming in more in the order of 100 milliseconds, and then P999, which is what I usually end up caring about, is where we hit disk. So on P999, then we're hitting a couple hundred milliseconds to generate your home timeline. Is because we've probably fallen out of cache for that particular user, and now we're actually issuing queries against platters in the data center. The question, of course, is how do we debug this? This Twitter architecture is converted from one that's a monolithic Ruby cluster to a SOA cluster instead. So trying to gather statistics across all the different services and aggregate them together has been a problem for a while. So we've created a system that we call Zipkin. It's based on Google's Dapper system. We've open sourced it, however. So for any particular request that comes through the data center, we can taint requests as it passes through the TFE and actually see every single service that they may possibly hit. So if I were to ask for all the requests that are generating home timelines, then I get traces that kind of look like this with the request time in the data center. So you can see we're doing about 68, 67 milliseconds in the data center in order to hit home timeline and hit all the different clusters involved. And if you were to drill down, then you can actually see every single request as we gather across the data center and actually understand all the different timings across them. So we spend a lot of time in memcache lookups. We have some TweetyPie hit down at the bottom where we're spending about 2 milliseconds in it, whereas the overall timeline request looks like 68 milliseconds. We've modeled this UI to look a lot like the web performance UIs that you see. And then we can actually see different annotations of the system. So we spend a lot of time debugging the system just by looking at interfaces like this to understand where all the time is going in all our requests. So if I'm trying to get a request to look like 10 milliseconds from a timeline service and it spikes up to 600 all of a sudden, I can start looking and finding a particular request that may have done that. And then we can also generate aggregate statistics across the cluster to understand what performance looks like for the fan-out process or for the delivery process. Getting something like the get activities user timeline down to 2 milliseconds is what it takes about 2 years of work in order to pull off something like that, because I spend all the time just fighting GC pauses, fighting memcache lookups, understanding what the topology of the data center looks like, and really setting up the clusters for this type of success. I know I went a little fast and I'm running a little early, so I apologize for that, but I'm basically happy to answer any questions about what these timelines look like or how we do performance or debugging at scale at Twitter. So given that, thanks.